All right, this is day 29. We are looking at lowest common ancestor in binary search tree. We're still obviously in the tree section here. This is the first time we're going to look at a binary search tree though. So just for a little context, as we start looking at the prompt, the difference, so the thing that makes something a binary tree is that it can have anywhere from let me back up. The thing that makes something a binary tree is that it's a tree where each node has 0 to 2 children. So up to 2, binary, right? 2 options. This is the first time we're going to be looking at binary search trees, which have one additional trait, which is that for every node in the tree, if it has a left child, the value will be smaller than the root. And if it has a right child, that value will be larger than the root. So that's guaranteed for every node in the tree. It starts from the root and it goes all the way down to the leafmost nodes. And this also has the side effect that the entire left subtree will be smaller than the root node, and the entire right subtree will be larger than the root node, which we're going to take advantage of today. Yeah. All right, so let's look at the prompt. It says, given a binary search tree, a BST, where all node values are unique and 2 nodes from the tree, P and Q, are given to us, we want to return the lowest common ancestor of the 2 nodes. They said... Okay, yeah, I was going to say they said BST and LCA and then just never used the abbreviations again, but they used them down here. I just thought that was funny. Okay, so they clarify a little bit for us what we mean by lowest common ancestor. It says the lowest common ancestor between 2 nodes P and Q is the lowest node in a tree T, such that both P and Q are descendants. And the ancestor is allowed to be a descendant of itself. And so this means if we have 2 nodes where the lowest common ancestor is actually one of the nodes, then we'll return that node. Okay. Now they're saying lowest, so really important idea here for the problem. They're saying lowest because if we're given 2 nodes in the tree, then the root itself is always going to be a common ancestor of the 2 nodes because the 2 nodes are in the tree somewhere, right? What we want is to go as deep into the tree as possible while still having both of the nodes as descendants. So let's take a look at the example. We might go through a couple additional ones. This tree is given to us visually here, and they tell us that P is 3 and Q is 8. What P and Q will really be are nodes in like actual objects that are in the tree that have values of 3 and 8. So in this case, we have this node here and this node here, and their only common ancestor is actually 5. So if we were to climb up the tree, the first time that we have something in common between those 2 nodes is 5. Let's take a look at what other example they give us. So we got this tree here, and the nodes are P is the 3 here, and Q is the 4. So again, any 2 nodes are going to have the root as a common ancestor. We want to go deeper into the tree, if possible, as deep as possible. So in this case, these 2 nodes, 3 and 4, they do have 5 as a common ancestor, but they also have 3 as a common ancestor. If we go anywhere else, so if we go on this side, these nodes are not related to 3 and 4 at all. If we go further over here, these are no longer related to 3 and 4, or they're not ancestors of 3 and 4. And if we go down here, 4 is an ancestor of 4, but it's not an ancestor of 3. So we have to go with 3 here. And again, we'll return not the value, but the node itself. And you can see from the typing here that we want to actually return a tree node. Okay, so they also tell us that the number of nodes in the tree will be between 2 and 100, which makes sense because we couldn't really have nodes that are between 1 node or between 0 nodes. So we need to have at least 2 nodes, and P and Q will both actually be nodes and actually be in the binary search tree. The values are between -100 and 100, not really a concern to us, we're not manipulating those, and P and Q will not be the same node, although I don't think that affects the solution that we'll talk about today. All right, so this is, again, the first time we're looking at the binary search tree quality, so we'll talk a little bit about that, and it actually is kind of a great piece of info for this particular problem. Okay, yeah. So let's, well, you know what, actually, let's talk about one more. Okay, hold on, let me think about this. Let me grab this image, and then we'll actually manipulate the example they gave us, so I don't have to like rebuild it. Ugh, unfortunately, it's going to be like light moded. I'm going to kill myself. Oh, I'm blind. Okay. All right. Okay, so here's the example image here. There we go. So let's talk about this a little bit. I think a good way to split this is, and this will actually pay dividends in some future problems. There's really only, well, I'll say that there are three main ways for this to work out. One is that the two nodes that were given are both in the left subtree. Ooh, hello. One is that the two nodes that were given are both in the left subtree. Okay, another one is that they're both in the right subtree, from the root, at least. And then the third option here is that one is in the left subtree and one is in the right subtree. And I'm talking about from the root, right? Okay, now if they're both in the left subtree, right, let's say it's 1 and 4, for example, then we know, again, that the root, that the overall root of the tree is an ancestor, but there is a better ancestor because we can go into the left subtree and the two nodes are somewhere in there, right? Similarly, if the two nodes are in the right subtree, then the root is still a common ancestor, but there's a better common ancestor somewhere in that right subtree, right? So this is going to tell us kind of how to traverse. And I think actually this is really great for us to think about because finally, the last situation is if one is in the left subtree and one is in the right subtree, then the only common ancestor they share is actually the root node itself, right? If there were any other common ancestor, it would have to be in both subtrees at the same time, and that's just not something that can happen, right? So we have sort of this default scenario, which is that the root is a common ancestor. If we realize that the left node is in the left, or one node is in the left subtree and one node is in the right subtree, then we're done. That's the only common ancestor that they have, and that'll be our answer. Otherwise, there's a better answer waiting for us somewhere in the left subtree or somewhere in the right subtree. So the question is, how do we figure out if the two nodes are both in the left subtree or both in the right subtree, or maybe one is on one side and one is on the other side? Well, because of the nature of binary search trees, we just have to compare their values. So what I mean by this is, let's say we did have this left-left scenario. Well, because of the way binary search trees work, we know that everything in the left subtree is going to be smaller than the value of the root node, or their values will all be smaller than the root node, right? So this provides a very easy way for us to check. Like if p.val and q.val are less than root.val, this is going to confirm to us that we should go left. Okay, on the other hand, let's say it's like 7 and 8 are the two nodes that were given, or the values of the nodes were given. So the alternative, or one alternative here, is that root.val is smaller than both p.val and q.val. And in this case, that's going to tell us basically go right. And the final scenario, which is this one where we have like one on the left, one on the right, again, because of how binary search trees work, there couldn't be any other common ancestor besides the root in this case. And how can we detect this scenario? Well, what we're saying quite literally here, based on the qualities of the search tree, is that one of the nodes is smaller than the root and one of the nodes is bigger than the root. And if that's the case, then we just return the root that we're currently looking at. And as with our previous solutions, well, actually, let me just kind of denote this in the diagram here. So if, well, there's a couple ways we can capture this, and we'll talk about how to do this cleanly in code, but if p.val Ooh, and since the node itself since nodes are ancestors of themselves, we would say if the root is between P and Q, so I'll say it this way. So we actually don't know which one is bigger or which one is smaller. So if this is true, or if this is true, then we already have our answer. We can return the root. Okay, now we've answered this from the sort of general perspective of like the whole left subtree and the whole right subtree. But these guys right here, I kind of encapsulated them as go left and go right. These require us to do recursion more deeply into the tree, right? So we'll basically repeat this question and ask, hey, where should we go next until we've found our answer? And since we've chosen 2 nodes from the tree, we're guaranteed to actually find an answer. We just need to keep going until we finally reach this scenario right here, which is both the solution and the base case. All right, and yeah, that's pretty much it here. This is very similar in nature to like when we did binary search as an algorithm, right? We were saying, hey, we can get rid of a whole half of the list and just look in the half that is relevant to us. This is the same idea. When we say go left, what we're saying is the answer to this problem couldn't possibly be in the right subtree. Let's look on the left-hand side. When we say go right, we're saying the answer can't possibly be in the left subtree. Let's look at the right-hand side. And then finally we stop when we find a node that is between those 2 values because we know we couldn't go left or go right to get our answer. All right, and that is pretty much it. Again, we'll talk a little bit about how to do this in the code, but in terms of the time complexity related to binary search as an algorithm, since we're eliminating half of the tree at a time, this is going to give us O of log n, specifically log base 2 of n, and that is the case for like trees that are filled level by level. So like if you had a tree, for example, so here's just like a worst case scenario. If you had a tree that looked like this, it's really more of a list, right? And in this case, we just have to look through all the nodes. We don't really get to eliminate anything. So there are like some convoluted scenarios that could cause this to be worse than log n. Like specifically, it could become linear, but never worse than that. But generally speaking, if the tree is like tree-shaped, so to speak, we're going to get log n time complexity. All right, so yeah, these are our 3 scenarios. Let's tackle the code. If anybody has questions, please let me know. But this is the overall algorithm, and I'm going to split view it so you can continue to like chew on this while I code it up. While we code it up. All right. So we'll start with the base case actually. Well, okay, here's how we can organize these like kind of several scenarios here. I'm gonna say small is the minimum between p.val and q.val. And then large is the maximum between p.val and q.val. Since we don't actually know which one is bigger and which one is smaller, this is just a nice way of like getting that information. Now, what we can also do here, since we don't need to like keep, like this is sort of like additional overhead that we really only have to do once. What we can do is make a helper function here. So we can say def LCA helper, for example. And what are we going to give it? Well, it already has access to small and large here. We really just need to give it another root. Okay. And we're just going to set up some of the like scaffolding here to make this happen. Now that we have small and large, we can do what? Return LCA helper with the root. Yeah. Okay, so now we've got like some of the structure for this. What we can say is our base case is this guy right here, and we can summarize it as if small is less than or equal to root.val, and root.val is less than or equal to large. Again, this means we've actually found our LCA. This is as deep as we can go. We can't go left and we can't go right, so this must be the answer. We will go ahead and return root. Okay, and then the recursive scenarios here, if both values are smaller than the root, so we can say elif large is less than root.val, we want to go left. And then finally, the last scenario here is that we need to go right, basically, so I'll just say else, although we could capture this with like if small is greater than root.val, but we'll just say else here. Then we are going to go right. And we want to return like the recursive solution to that, because eventually we will hit the base case and we'll get a root returned from that. So we want to kind of carry that up the levels of recursion. All right, and I think that's it. I'm sure I messed something up. I don't know what yet, but I guess we're gonna find out. Yay. Yippee! Ah! Okay. Is that the sound? Did I do that? Was it good? Is that what I'm talking about? No, I was talking about the autism creature. I'll have to look it up. I don't remember what it sounds like. Anyways, so yeah, that's that. And honestly, this part right here, the small large, like we don't really have to do that. This is just a nice way to kind of like cleanly explain which pieces we're working with. And then we don't have to like recalculate this every single time. Those values actually stay the same as we go through the problem. So yeah. Let me think. We already talked about time complexity. There's no extra space used here. Well, there's constant extra space because we do this once just to like make it a little bit cleaner. And that's that. So this is very much doable without the helper function. I just think that the helper function cleans it up a little bit, makes it a little bit more understandable, and reduces a little bit of overhead from doing this whole min-max thing. Great, well that's that. I think the rest of the problems here all deal with binary search trees, which is really common. Like it's sort of unusual to be asked about just a general tree. Binary search trees, because we got this additional functionality, are more commonly asked about, I would say. Great. Well, that's that for today. Thanks for tuning in. I'm going to the gym now. Have a good night, you guys.